Good afternoon, everyone. I'm here to discuss the evolution of 8260 with you. Here's an agenda of what we will cover in this discussion. A quick overview of EPA method 8260, advancements in automated sampling and purge and trap, advancements in GCMS technology, and finally, how we utilize these advancements for the environmental testing industry's needs. So EPA method 8260 is a way of analyzing volatile organic compounds, also known as VOCs, by gas chromatography and mass spectroscopy. It is applicable to nearly all types of samples regardless of water content. With this method, we can analyze for well over 100 organic compounds. There are various techniques for sample introduction, including direct injection, cryofocusing, headspace analysis, and purge and trap by method 5030 and 5035 for soils. For the purposes of today's discussion, we will focus mainly on the purge and trap technique. The definition of purge and trap is an analytical technique designed to efficiently extract VOCs from a matrix and concentrate them for transfer onto a GC analytical column without sacrificing peak shape, recovery, or accuracy. This extraction is done by bubbling an inert gas through a portion of the aqueous sample at ambient temperature, and the volatile components are efficiently transferred from the aqueous phase to the vapor phase. The resulting vapor is then swept through a sorbent column, what we commonly refer to as a trap, that absorbs the volatile components. After purging is complete, the sorbent column is backflushed with inert gas to desorb the components onto a gas chromatographic column. The same process is repeated for soil samples by adding organic-free reagent water to the soil sample and purging it directly in a purge chamber. This is most commonly done by purging the sample vial itself. For what seems like such an easy, straightforward process, there are a number of issues we run into with method 8260. The biggest issue in the whole process is water. Obviously, getting water or moisture into our GC or MS would be detrimental, so we need to eliminate as much as possible during the purge and trap concentration step. Even a little bit of water produces poor peak shape in the MS and low recoveries in water-soluble compounds. There are also a large number of poor performers and problem compounds. The actual EPA method itself labels a large number of compounds that exhibit known difficulties with reproducibility, response, recovery, stability, and/or chromatography. The inert gas we use has also become an issue because of the helium shortage. And finally, time is always an issue in a production environment. More samples equals more revenue. There is always a need to maximize efficiency in environmental testing. So how do we overcome many of the issues that have plagued method 8260? Let's take a look at improvements in chemical testing equipment technology. First, we will look where the whole testing process starts, with automated samplers and purge and trap concentrators. As you can see from this slide, automated sampling has come a long ways from where it was even a few decades ago. Even with just a few pictures, you can see a lot of progress. We even still have a few of these older samplers in our network today. I know I've worked on a lot of Archons over my time in this industry. There have been a number of significant improvements in automated samplers. We no longer have to hand load samples into sparge tubes, like the ALS 2016 from the previous slide. We have inline inkjet style internal standard and surrogate edition. Sample capacity is also increased. Most new automated samplers can hold around 100 samples. We can run water or soils on dual sample type and auto samplers that are now available. Inline sample dilution capabilities are also possible, as well as inline sample pH recording coming off the waistline. Updated software provides better communication between automated sampler and concentrator to the GCMS. This saves time on sample transfer between all components of the testing process. Automated samplers are now more efficiently engineered as well to save time on troubleshooting issues that may arise from extended use. We can utilize nitrogen as a carrier gas, and software upgrades have made it easier to schedule and keep track of samples. After the sample has been taken from the automated sampler, it's sent to the concentrator. As you can see here, concentrators have also undergone a lot of changes in the last few decades. In fact, I think I've worked on almost every iteration of one of these concentrators in my time in the industry. As I said earlier, removing water from the sampling process is one of the biggest keys to success in method 8260 chromatography. Concentrator moisture trapping systems have evolved over time to increase water removal during the desorbing process that sends the sample over to the GC. Also, sorbent trap material has become better at retaining problem compounds and keeping them moisture free. Heated zone control for the mounts, valves, and sample pathways has become more advanced with upgraded software capable of controlling and monitoring areas to keep moisture out of the concentrating process. Concentrators also offer bake program capabilities that allow time and bake flows to be set to help reduce carryover and keep the system moisture free. Newer concentrators now have advanced flow control and can utilize nitrogen as a purge gas. Flow control is no longer manually controlled, but is controlled electronically by the software. This allows for leak checking and troubleshooting through the software. We can utilize nitrogen as a purging and carrier gas, which really saves on helium usage. Flow control is allowed for quicker, more efficient purge times. Higher purge flow means less purging time. This decreases runtime and increases sample capacity. In fact, studies have shown that increasing flow and reducing purge time has minimal effect on compound recovery. As you can see from the data below, from a study on purge time and purge flows, that recoveries for compounds vary only slightly when increasing purge flow and decreasing purge time. Next to the data, you can see that the chromatographs from the study show that there is little difference in peak resolution. Newer, up-to-date concentrators also offer upgraded software. They are no longer controlled by tethered handheld devices, and some even offer Bluetooth compatibility for out-of-lab monitoring. We are now capable of setting and monitoring all flows and temperatures in the concentrator. They come equipped with alarms for any parameter that deviates from the method settings, so that you can immediately fix the concentrator if something happens. With all this, concentrators have better communication as well between the automated sampler and the GCMS, which helps decrease runtimes by keeping everything in sync. There are several other upgrades that newer concentrators offer. Heated purge allows samples to remain the same temperature regardless of room temperatures. This is helpful because temperature fluctuations can affect compound recovery. Some new concentrators come equipped with a foam detection sensor on the sparge tube that will shut it down in the presence of foam that is detrimental to the concentrator itself. They also now come equipped with hot water reservoirs that rinse the sparge tube and help keep the concentrator clean. Concentrators are now smaller as well and take up less lab bench space. They're also better engineered with reduced sample pathways, making maintenance and troubleshooting much easier. Moving on to the next part of the 8260 sampling process, we will talk about gas chromatograph and mass spectrometry advancements. So once a sample is finished purging in the concentrator, it is desorbed to the gas chromatograph. As you can see here, even the GC ovens have improved significantly over the years. GC oven controls have gone from touchpads to touchscreens. They are all now equipped with electronic pressure control, also known as EPCs, which means you no longer have to manually adjust gas flows by hand-turned dials. You can utilize gas saving mode to help save helium usage. They have more efficient split modes for the injection port to reduce sample load and to help preserve column and filaments in the mass spec. EPCs are much more compact now and easier to troubleshoot or replace. They have increased longevity and reliability against gas contaminants. Some GCs offer a more compact design, also known as a micro GC, like the Agilent 6850 and the new Intuvo design. Newer, up-to-date GCs offer network compatibility for better communication and data transfer. Upgraded software makes scheduling and loading samples much easier and more efficient. We can now monitor the health of the system by tracking injections and consumable usage with the use of Agilent Smart ID keys. We also have remote connectivity, allowing users to check on the system when outside of the lab. Injection port design on GCs has also changed. New design features making changing out liners and seals much easier. Agilent offers self-tightening injection port and detector nuts for quick and efficient column installation. Newer septa for the injection port are also more inert and reduce septum bleed. With all the changes in newer GCs, we have also had upgrades in GC consumables. Injection port liners are more inert, and proprietary coatings have helped compound recovery and chromatography. Advancements in column production have allowed for microcapillary sizes and widths. Capillary coatings have also been optimized specifically for method 8260. Shorter length columns have also helped decrease GC runtimes. After our sample has been separated out by the GC evident column, it is now analyzed by the mass spectrometer. Once again, we can see in the pictures of these mass specs that there have been significant changes over time. In the last few decades, improvements in mass spectrometry have continued to advance drastically. Changes in quantitative accuracy, mass spec resolution, and data processing abilities have helped push the environmental testing industry to new heights. Here's a nice little diagram of the physics behind mass spectrometry, including some of the things we will talk about that have changed in the mass spec over time. Most mass spectrometers come equipped with a stainless steel source, which will work for method 8260, but advancements in source types have had great effects in testing efficiency for this method. You can now get an inert ion source, which increases sensitivity and accurate quantitation by keeping the sample path and detector surfaces indoors. To look even lower, you can get an extractor EI source that has an extractor lens in place of a draw-out plate, which is also made of inert material. This provides enhanced response for active compounds and late eluders. Mass spec source draw-out lenses now come in a variety of sizes. 3mm, 6mm, and 9mm are all available for use in most mass spec sources. Through testing, it has been found that the 6mm lens has shown to be a more robust option for method 8260. 6mm lenses have given better percent RSD recoveries and calibration curves, especially on poor responding compounds. As you can see from the study presented on this slide, the 6mm draw-out lens showed excellent calibration curve RSDs for a number of compounds, including problematic compounds like chloromethane, vinyl chloride, TBA, bromodichloromethane, and many others. The newest mass specs available now come equipped with a triple access detector electron multiplier. At given operating gains, it provides higher signal intensity by collecting more ions from the quadrupoles. Although the signal is enhanced, neutral noise is substantially reduced through the off-access design. Detector lifetime is also increased under proper operating conditions. This provides many benefits during sample analysis, including enhanced detection limits, increases in compound relative response ratios, calibration curves with greater slopes, and lower tuning voltages, increasing the lifetime of the multiplier. In this slide is a picture of an old electron multiplier that you could find in the older versions of mass spectrometers. And then on the right is a picture of the new triple access detector electron multiplier. As you can see from just looking at the pictures, there's a huge difference in the way these detectors work. Below, you can see a graph with the differences in signal to noise between the old multipliers, the dotted line, and the new multipliers, the solid black line. You can tell that the signal to noise difference is huge. This is really helpful when we're looking at lower concentrations in our samples. Mass specs have also been upgraded in other significant ways. They have gone from using diffusion pumps to turbo pumps to pump down the mass spec chamber. Older diffusion pumps required oil changes and much longer times for heating and cooling. A turbo pump also seals the mass spec chamber better with less contamination, and turbo pumps are also more robust. They last longer and require less maintenance. Newer software has made tuning the mass spec easier and more efficient. Newer mass specs take far less time to tune. The software also allows for all kinds of parameters to be monitored and changed, which is helpful in method development and optimization for method 8260. Mass spec analyzers can also handle higher temperatures, which is helpful in compound resolution and removal of contaminants in the sampling process. Also, over the evolution of mass specs, the GC to mass spec transfer line has been improved to ensure that analytes are purged directly into the source. Source cleaning materials and procedures have also improved over this time to ensure that sources are kept reflective and to reduce scratching and scarring when cleaning the source. You can now get a magnetic rough pump that helps pump down the mass spec chamber. These offer the same vacuum of the traditional rough pumps we've used over the years, but with less need for oil changes and maintenance over their use. Mass production of mass specs has also led to readily available parts and reduced pricing, which is great because the environmental market has been driven towards more production, which means more samples at lower prices, requiring more instrumentation and more parts on hand to reduce downtime and maximize instrument use. So now that we've gone through all of the advancements in the sampling process for method 8260, let's discuss how to utilize these advancements for industry needs. Improvements in automated sampling, sample concentrators, and GCMSs throughout the years has led regulators for method 8260 to lower their reporting limits on a number of compounds. So now most of the labs in our network calibrate at sub-part per billion levels for all of their compounds. Below is a snippet of one of our lab's calibration curves, showing that several compounds can calibrate from 0.2 ppb to 250 ppb. I've included some of the most common compounds for method 8260 here. You can see that vinyl chloride, MTBE, benzene, ethylbenzene, and the xylenes, we can get to curve under 20% RSD for all of those compounds. With the advancements in 8260 sampling technology, we have also optimized sample-to-sample runtimes. We have done this by utilizing software on newer instrumentation to ensure the sampler and concentrator are operating in sync. We have also shortened purge times by optimizing purge flow, like I showed you earlier in the concentrator slides. We've also decreased the desorb time to minimize moisture getting into the GC and mass spec, which can be detrimental to the system and also can hurt recovery for compounds in the 8260 sampling process. We've used advancements in system consumables to optimize recovery and continually keep the system free of contamination. We've exploited advancements in GC columns to decrease runtimes and optimize compound separation. Optimization throughout our lab network makes our average 8260 analysis sample-to-sample runtime between 14 to 20 minutes, which is ideally between 80 to 100 samples per instrument per day. Here is an image of concurrent sample sequence runs that highlight a 14-minute sample cycle time. This is great in an ever-increasing production industry. We have also been able to utilize new technology to reduce our helium gas usage. By applying automated sampler and concentrator nitrogen gas options for carrier and purge gas use. We have optimized GCMS method settings to reduce flow of helium during sample runs. We couple that with the gas saver options now available on GCs to also reduce helium usage. And newer EPCs reduce helium loss, optimize flows, and keep our instruments clean from contamination. One big initiative that Pace as a company is pursuing is what we call easy soil. By leveraging the technology advancements now available for chemical testing equipment specific to Method 8260, we have created a method to eliminate running low-level soils that purge and vial. Why is this significant to the industry? Well, it increases productivity in the lab and in the field because of decreased sample volume needed. It reduces turnaround time from 2 days for preserved sample soils to 14 days. It also improves data quality and reduces the overall carbon footprint that we put out for both our clients and our company. So, using the advances made in testing equipment, instrumentation, and consumables, we have been able to enhance Method 8260 to be more efficient, provide better data, and reduce our overall carbon footprint. As the industry pushes towards more production and lower compound reporting limits, we have been able to leverage the progress made on testing equipment to increase sample loads and look lower than we ever have before. The evolution of 8260 has been a direct response of increasingly changing technology and the environmental testing world's needs.